Right, folks, eigensystems now. So we are moving further in our exploration of matrices, and this is pure quantum mechanics and vibrational spectroscopy. Second and third years have seen this in various shapes and forms, so they will find a welcome explanation as to what it was that we were actually doing. First years, we will see a lot of that when you are dealing with vibrational modes. We will be looking at different molecules and we will be treating them as little balls connected by strings. And then the eigen problem will appear as a problem of determining what the vibration frequencies are and which atomic motions they correspond to. And then when all of you do molecular orbital theory, so reasons why benzene can be nitrated on all 6 positions, but when it's phenol, it's preferentially nitrated on 3 out of the remaining 5, and so on. So these sorts of chemical reactivity predictions hinge on molecular orbital theory, which will, after quite a few lectures by Marina, I think it will be in your second year, eventually distill down to an eigenproblem. So again, we are preparing you for what is yet to come in your various chemical applications. But the first thing for today is a little bit of a side venture into a function of a matrix that occurs time and again everywhere across linear algebra. And the reason for that is this particular function is an indicator of sorts. When it's equal to 0, that means matrix is degenerate. When it's equal to +1, that means the matrix is a rotation. -1 reflection, and there are other things about matrices that this tells us, and the function is called determinant. Its rigorous definition for a matrix that is n by n is very complicated, and we will not go there. We don't have the time in this course. But what I will do is give you the expressions and some discussion for the 2-dimensional and the 3-dimensional case, which is what you realistically will encounter in your workshops. If you are faced with a determinant of a matrix that's 4 by 4 or bigger, just use a computer. What is important is that you understand what this is and how to use it. So a determinant of a 2 by 2 matrix, A, B, C, D, is the product of the elements that are on the diagonal, so AB, minus the product of the elements which are on the counter diagonal, B, C. In a schematic way, it's this, with a plus, and then this, with a minus. A determinant of a 3 by 3 matrix is a lot more complicated. Determinant A, B, C, D, E, F, G, H, I. The schematic form of it is you take a product of the 3 diagonal terms and you take the product of the triangles in here that have the base that is parallel to the main diagonal. This triangle, the base is parallel to the diagonal, and then that triangle. That goes in with a plus, and then the product of the elements on the counter diagonal, that, and that. This product, and the triangles with the bases which are parallel to the counter diagonal. Goes in with the minus sign. That's the best way I know to actually memorize this. Now, if we are to examine 3 by 3 determinants, this will be provided. And again, perhaps to somebody who has other priorities than doing mathematics his entire life, this is perhaps harder to memorize. And so, if we go into here, right, A times E times I plus BFG plus DHC minus counter diagonal CEG minus counter diagonal parallel to base DBI minus FHA. So that mnemonic actually straightforwardly allows you to calculate the determinant. What is important to us, however, is not these explicit expressions, but the properties of determinants. So the first important property is A minus 1, so the inverse matrix, exists only if the determinant of A is not 0. So it's an indicator function that tells us whether or not we should even try to invert a particular matrix. The second property is that an equation AX equals B has a unique solution. If and only if the determinant is not 0. The special case of this that we will encounter today in a few minutes is something like this. AX equals 0. Imagine that you have a system of equations like this. Well, it's not obvious that this should be in any way unusual, because of course we've seen many systems of equations where the right hand side is 0. However, from the previous statement, if the determinant of A is not 0, then this system will have a unique solution. And of course, that unique solution, you can easily tell me what it is. It is the case of an all-zero vector. Because if we multiply a matrix by a 0 vector, we will get a 0 vector. So that's a solution. And because it's unique, that's the only solution. Such solutions are not terribly interesting, because they correspond to either there being no particle in the system at all, or the universe being empty, all sorts of boring scenarios. And so this has, people say, are non-trivial solutions. If the determinant of A is 0. If B is interesting, so not all zeros, then we want the determinant to not be equal to 0. However, when it is 0, we don't get anything interesting unless we actually demand that the determinant is 0. So it has these useful properties that will come handy in a moment. And the third one is if you have a 3 by 3 matrix, and the determinant of A is plus 1, that means that matrix is a rotation matrix. If the determinant is minus 1, it's a rotation plus reflection, either preceding rotation or immediately following rotation. So that is determinants. And let us now put them to good use in what is called a matrix eigenvalue problem. If you think about physical objects in general, if you look at a music string or a musical instrument, when you pluck it, it emits certain specific frequencies. Not just any random frequency. No matter how you pluck it, you still hear the same frequencies, or certain combinations of them overtones. If you look at mechanical systems, they have certain recurrent patterns of behavior, which are in some sense intrinsic to those systems. Pendulum swings, ball rolls, various things resonate and oscillate. For example, bridges have certain resonance frequencies, which, as you know, are best avoided unless you want that bridge to collapse. Similarly, molecules have molecular orbitals that are intrinsic to those molecules, and so on and so forth. So it stands to reason that physical systems have reproducible and in some sense intrinsic patterns of behavior that are characteristic of those systems alone. It turns out that the mathematical formulation of this principle is in fact called eigensystem. In particular, we would like to solve a problem that looks like this. If we have a matrix and we multiply that matrix into a vector, we want to know under what circumstances do we get that vector back, perhaps multiplied by a number. Such situations occur rather a lot if you have a rotation around the z-axis, for example. So a coordinate system x, y, and z. And we start rotating this coordinate system around z. Most vectors will be moving in various complicated ways. However, there will be one vector, or rather one specific direction, that this rotation will not affect. And this is any vector that is pointing along the z-axis itself. So, this rotation will not influence this. And so we can then say that, okay, we have a rotation around the z-axis by an angle phi. As you know from the previous lecture, this is actually a matrix. And when it is applied to a vector here, x, which is pointing along the z-axis, we will get that exact same vector back. There are things like translation and scaling where certain vectors don't change. There are things like differentiation. If we go d by dx, that's an operator, it's an instruction to do something to a function. Which functions would remain unchanged? Well, we know those are exponentials. In most general case, complex exponentials. And so this is ik e ik x. Again, this function, it's called a plane wave, was unchanged, only multiplied by a number. If we look at other derivatives, so for example, second derivative, d2 by dt squared, this is, as you know, an acceleration operator, because the second derivative of coordinate is an acceleration, acting on sine omega t, so on oscillatory functions. As you know, this is minus omega squared sine omega t. The function remained unchanged. It only got multiplied by the square of its frequency and a minus. So there are classes of vectors that remain unchanged under rotations. There are classes of functions that remain unchanged under coordinate derivatives, and classes of trajectories that remain unchanged under the time derivatives. So things like that needn't necessarily apply to vectors. They could be functions, but essentially we are looking for things that remain thus unchanged. Okay, how do we solve this? Let's say we have this matrix A, and we would like to find out what its vectors are. Now, such vectors are called eigenvectors. And eigen is a German prefix that signifies ownership. So these vectors are in some sense intrinsic to the matrix. And these numbers, and there are many of them, are called eigenvalues. If you are looking at various physical things, lambdas will be the vibrational frequencies of your molecules, x will be the corresponding displacements. If you look into quantum mechanics, lambdas will be energies, x will be molecular vectors. If you look at the bridge resonances that destroys the bridge, these will be the resonance frequencies, these will be the displacements of the various parts of the bridge. If you're looking at this, this is the momentum operator in quantum mechanics. These are the possible values of the momentum that the different wave functions correspond to. This is a part of the vibration equation, so the equation that describes oscillations of strings, and sine is one possible oscillation of a string. So this is all connected to physics. Let us now drop the physics and look at how to solve these things. Let us move that over to the right, to the left hand side. We will have ax minus lambda x equals 0. We can take x out of the bracket, but then we will have an interesting problem. We will have a minus lambda x equals 0. This a minus lambda is a nasty object. It's a matrix minus a number. It's not possible to subtract a matrix from a number. So let's do the following. Let us put something in here that doesn't actually change this. What I'll do is I'll insert a unit matrix into here. So this is a matrix with ones on the diagonal and zeros anywhere else. Unit matrix doesn't change the vector. When you multiply a vector by a unit matrix, the vector remains the same. So this equation is actually in every sense identical to the original solution. And so the unit matrix goes into here, and then ultimately goes into here. But now it's a unit matrix times a number. And so we actually have matrix minus a matrix, and we can now proceed to do that. Okay, what we now have is the need to solve this, and we would like to find the x. As per here, however, if our matrix is not degenerate, if that has a unique solution, then we know what the solution is. The solution is 0. This is a valid solution. This corresponds to the empty universe in the case of quantum mechanics, no vibrations in the case of a bridge, and no oscillations of strings in the case of the string oscillation. Perfectly valid solution, although fairly boring. If we should like to have a non-boring solution, we must demand that the determinant of that be not corresponding to a degenerate matrix, so the determinant must be 0. So it follows from here. So to be interesting, which is a strange requirement to impose on a mathematical problem, but okay. Determinant of A minus unit matrix times a lambda must be 0. Okay, what does this tell us? If we go back to the definition of the determinant, it's basically a polynomial. It's a bunch of matrix elements multiplied together. What we will have here is this matrix. We know it's a bunch of numbers. These numbers we don't know, but they will mix into the matrix and then get multiplied in complicated ways. What we will get in here is some polynomial of lambda, quadratic polynomial in the case of 2 by 2 matrix, cubic polynomial in the case of 3 by 3, equals 0. Basically either a quadratic or a cubic solution. Nice and easy. So, simple equation for lambda, which will have, in the case of 2 by 2 matrices, 2 solutions, and in the case of 3 by 3 matrices, 3 solutions. So that gives us lambda k. 3 of them or 2 of them, but we will enumerate them with k. As soon as we know them, we can put them back into here. So this is known. This goes back into the equation. Ax equals lambda kx. And we get the corresponding x out. X, k. Which sounds like we've solved the problem. However, remember this example I gave you. This direction remains unchanged. So a vector of length 1 will be an eigenvector, but a vector of length 2 would also be an eigenvector. Right? It remains unchanged. And so this will have a certain amount of liberty in it, in that its length, and even direction, would be arbitrary. So the last thing we would have to do in this flowchart is we would want to normalize this vector. We would want a vector with the length of 1. So our stage is normalization. And then we know what we wanted to know, either the molecular orbital or the normal modes or the oscillation frequency or any such thing. So let me go through a complete example of this. for a 2 by 2 matrix, excuse me, that you can have this illustrated completely from the beginning to the end. So we can cut this off. Let us do something like that. Okay, so our task is to find all eigenvalues and eigenvectors of the matrix that occurs in the theory of magnitude, so-called Pauli matrix. 1/2, 1/2, 0, 0. So we would like to know which vectors, two vectors, when you multiply them by this matrix, give you those vectors back. Alright, so we do that entire thing. What this means is 0, 1/2, 1/2, 0, minus unit matrix 1, 0, 0, 1 times lambda x equals 0. So I shifted this over there. I took x out of the bracket and I inserted that unit matrix. Okay, well, matrix times a number is, we simply multiply every element by that number. So lambda, lambda. And now, in order to have interesting solutions, we must have the determinant of this equal to 0. Determinant of first element minus lambda, second element 1/2, third element 1/2, and the last element minus lambda. Must be 0. As per the definition of our determinant, product of the diagonal, so lambda squared, minus the product of the counter diagonal, equals 0. In this case, trivially easy to solve. So our lambda is plus or minus 1/2. And these are their eigenvalues. For those of you who will be doing magnetic resonance option module, this matrix is the Pauli matrix corresponding to X magnetization. These are the two projections of the spin on any specified direction. You know that the electron has a spin half. If we used the usual Pauli matrix, the Z, it would have been pointing up or down. In this case, it's pointing left or right along the direction of the x-axis, but it still has two projections, plus or minus a half. So that basically corresponds to taking your usual molecular and atomic orbital diagrams and turning them 90 degrees, so electrons start pointing left and right, with the up and down. Okay, so these are the two values for this mathematical abstract problem of just the lambda, and for the physical problem underneath it is actually the projection of the spin. Let us now go to the next stage. So we got lambda k, so we got here. Let us now calculate the corresponding eigenvalues. So I'm returning back there, and I'm saying, all right, 0, 1/2, 1/2, 0, x, and let's just call it AB, equals, let's take plus 1/2, plus 1/2, AB. Okay, that's the system of equations, and I showed you in the previous lectures how to go between the standard notation for equation systems and the matrix vector notation. In this case, to straightforwardly solve it, actually makes sense to go back to the usual sort of school kid notation for it. And what we can say in here is 0 times A plus 1/2 times B equals 1/2 times A. So that times this, and sum up 0 times A, half times B equals the corresponding element of 1/2 A. And then 1/2 times A, so that plus 0 times b equals 1/2. This system of equations has an interesting property. The first equation, if we remove all the 0 terms from here, basically says b equals a. Second equation says a equals b. These two equations are identical. The second equation doesn't tell us anything new. This is the result of us demanding that the determinant be 0. Remember what I told you in the previous lecture. When the determinant is 0, matrix is degenerate. That means its columns or rows are linearly dependent. And we actually saw this manifested in here. The two rows in this case are exactly the same. Of course, this only tells us now that A is equal to B. And so we don't have enough equations to actually define them. And this is the reason behind that picture over there. The length of the vector is arbitrary. There's an arbitrary parameter in there. So if we have A equals to B, vector AB can have any length, but the direction is, of course, specified. What we need to do is to add the normalization. We need to add the condition that the vector has to be of the unit length. And so that gives us the missing equation. So now we have A equals B, which is what we got. And the second is A squared plus B squared equals 1, which is the condition for the vector to have the unit length. Okay, from here it is reasonably easy to solve. If we substitute all b's with a's in here, we will have 2a squared equals 1, which means a is 1 over root 2 plus or minus, and then b is exactly the same. B is equal to a. Now remember what I told you about the direction. The direction of the eigenvector is arbitrary. If it's pointing up, it will remain unchanged. If it's pointing down, it will remain unchanged. So don't worry if you are off the answer by a minus when you do an eigenvector, because it's still a perfectly valid eigenvector. So let's pick the positive direction, and then our x will be 1 over root 2, 1, 1. Right, so A is equal to B, and the total length of the vector is unit. Okay, so this was our first lambda. So let's call this x1, and lambda 1 is 1/2. Let us now go through the same procedure for lambda 2. Equals minus 1/2. So we write the whole thing from the very beginning all over again and get ourselves the second vector. So the original problem, for which we now know the lambda, was ax equals lambda x. So 0, 1/2, 1/2, 0. We will call it again AB equals minus 1/2 AB. Okay, converting matrix vector notation back into a system of equations. 0 times A plus 1/2 times B equals minus 1/2 A. Second equation, that times the second row, half A plus 0 times B equals minus 1/2 B. And the normalization condition, A squared plus B squared B1. Just as before, the first equation is exactly the same as the second one, except now B is equal to minus A. Substitute it into there. A equals 1 over root 2, taking the positive direction, and therefore B is minus 1 over root 2. And so the conclusion here is our second eigenvector, 2 is 1 over 2, 1 minus 1. And after 2 is minus 1. The last thing that remains is to actually check this. When you are doing these problems in practice, as you can see, it's a fair amount of writing and reasoning and calculating. Never stop until you actually check this. So let us check. 0, 1/2, 0. Acting on, for example, 1, 1. The length of the eigenvector doesn't matter, we just conventionally normalized it, so we must get this vector with a coefficient of 1/2 in front of it. Okay, that times that, 1/2. That times this, 1/2. Which is indeed 1/2 times 1. So we took the eigenvector, we got the eigenvector back, and the coefficient is the corresponding eigenvalue. The same goes for the second one. Okay, so this is rather important, so let me just go through the entire philosophy and the entire procedure again. So there is a number of problems across physics which all share the same formulation. Take a matrix or some operator times a vector or some function returns you that vector back multiplied by a certain number. In order to match the topology on either side, this is matrix vector, but this is scalar vector, we just put a unit matrix into here, which doesn't change anything, it multiplies it, so we can just put it. Okay, then we can move that over to the left-hand side, we get this. We take x out of the bracket, we get this, which immediately presents us with a dilemma in that we actually know the solution to this is a zero solution. For it to be a non-zero solution, we must demand that such a system has many solutions. Demanding that it has many solutions is equivalent to forcing its determinant to 0, which we must then do. So the determinant of that thing in bracket must be 0. Because lambda goes into that mid-grinder, that the determinant is, it produces an equation for lambda, which we can solve for all those lambdas, which this gives us the eigenvalues, which is already half the problem. As soon as we know the eigenvalues, we can put them into here, substitute the actual matrix, and try and solve it for the vector, which I did in here. So lambda, lambda, and then we found the lambdas. And so, okay, that's the original matrix, that's the vector, that's the lambda, and that's the vector. And it looks like a reasonably good system of equations, which we can write out as a system. But then what we discover is consistent with us demanding that the matrix be degenerate. It actually is degenerate, in that the two equations that this yields are exactly the same. This will always be the case. Out of the many equations you will be getting in this procedure, there will be some that you don't need. Okay, but at least it allows us to conclude that A equals to B, so we know the general direction in which it's going. And then conventionally people write eigenvectors in a normalized form, so we just take the unit eigenvector, in which case the ambiguity disappears insofar as the length is concerned, but there is still ambiguity in the direction, so don't be afraid of the minus signs in the eigenvectors that you've got. We put it in, we say A equals B, and then the normalization gives us the second equation, a squared plus b squared is 1. All of that we can solve now for A and B, and that's our first vector, and an identical procedure gives us the second. So in your workshops you will have multiple examples of 2x2 and 3x3 problems of this kind. They are boring. I never do it by hand except in these classes. Of course, I ask the computer to find the eigenvalues and eigenvectors for you. There are commands in Mathematica, in MATLAB, in any language you like. But it is important for you to do it once or twice so that you understand how that is actually done. Right, so this was the matrix vector problem. Now let me jump rather far ahead and solve an identical problem for a quantum mechanical operator. Now, the chemists will explain in due course where the operator comes from, but to us it's just a derivative. We know how to do it. So just take my word for it that there is something called a Hamiltonian in quantum mechanics, and it's a bunch of derivatives. So it's a hat because it's an instruction to differentiate. Acting on some function, psi of x, will give us the energy of that function and the function itself. As you can see, the notation is virtually identical to there, except this is now something from quantum mechanics, and this is now the corresponding energy. We will go and say that a wise textbook, for example, Atkins, told us that the Hamiltonian is 1 over 2m dv2 by dx squared. So this is actually the energy of a particle that moves around, momentum squared over 2m. And then we will put the particle into a box of length a. So that's 0, that's a, and the particle will be living in that box as a probability density. But what's important is the box is really tough and has infinitely high walls, and so the particle cannot escape. So necessarily we must have psi of 0 equals 0 and psi of a equals 0. Basically, it cannot penetrate the wall. Okay. Now, this is a slightly different type of an eigenproblem. We previously had an eigenvector of a matrix. Now we have an eigenfunction of a derivative. But the principle is exactly the same. So let me write that down. So minus 1 over 2m d2 psi by dx squared equals e psi. It's a differential equation. It says, okay, find us such a function which, if you differentiate this twice, gets us the function back. You know perfectly well which functions we get back if we differentiate them twice with the sines and cosines. So I will not go to the nitty-gritty of how to solve this. This is, in fact, lectures 6 and 7 in this very module. So we will get there. For now, I will simply ask you to take my word for it that these are sines and cosines. Moreover, in here, if we write that down, d2 psi by dx squared is minus 2m e psi. Remember that when we differentiated that sign twice, we had omega squared coming out. So if we have root of this under the sign, then it will come out twice and we'll get this. And so the solution to this is actually fairly simple. It's some arbitrary number, I'll call it alpha, cosine root 2e x plus another arbitrary number beta sine root 2x. You can check it by direct substitution into here. If we take the second derivative of the cosine, the root will come out with a minus, then we take it again and the root will come out again, so we'll get that with a minus sign, and the same goes for the other trigonometric function in here. So it can be directly checked that this in fact satisfies the equation. The second thing that we must have is that our particle should not be able to escape the box. So psi of 0, cosine of 0 is 1, so that's alpha. Sine of 0 is 0, so that's just alpha, and that must be 0. So that means the cosine term is gone. We are only left with the sine. So our sine of x is actually beta sine root 2x. So that simplified life a little bit. The second thing that we've got is psi of a must be 0. So we must have additionally beta sine root 2 and A must be 0. Well, that gets us rid of beta because we can just cancel it, and under which circumstances is sine equal to 0? It's equal to 0 when the argument is pi by 2, no, 0 or pi, so basically a multiple of pi. So that means root 2 m A must be pi n. M is an integer. Take the square of both sides, 2m e is pi m over a squared, and therefore e is pi m over 2m a squared. Let me see if I haven't made any mistakes on the way. Pi squared and squared. Once we take the square over 2ma squared. So we actually figured out the energies, and this is called quantization. Turns out that once we impose constraints on the problem, so we confine the particle into a box, it can only have specific energies corresponding to that. And this is our eigenvalue. And just as we have multiple eigenvalues for the matrix, now we have multiple eigenvalues for the operator. Matrices were nice because we had, well, 2 or 3 eigenvalues. Operators are nasty because we actually have infinitely many eigenvalues. As you know, atoms can be excited to an infinity of possible excited states, and the same applies to a particle in the box, any confined system really. So we do have multiple eigenvalues, and this is called En. So then the corresponding eigenfunction is that, and we can plug our newly discovered energy into there. So then what we will get is psi n, so the n's eigenfunction will be beta sine, once you've done all the simplifications, pi n x over a. And this is the quantum mechanical wave function of the particle in the box. Beta is the normalization constant. We will get to function normalization a couple of lectures from now. But this is an example of an eigenproblem that is not about matrices and vectors, but instead is about derivatives and functions. And you can see I sort of deliberately put things in roughly the same location on the 2 boards, is that the difference between them is actually nominal. You can view function as a very long and very densely packed vector, in which case that problem actually becomes identical to this. This is called a representation problem. You can sometimes represent functions with vectors and the other way around, but we don't have the time to really go deeply into it. Okay, so the summary of the lecture, yeah? This will be haunting you forever, till you retire, and in my case, even after that. If you're a chemist, we've introduced a little diagnostic function called determinant. You must have seen this before somewhere. And it has a few properties which I just gave you without proof. That the inverse only exists for matrices with a non-zero determinant, and the problem solution is a unique solution in that case. Turns out that we actually don't want that to be true, so we have to demand that determinant is 0 in here. So the matrix problem, I've already gone around twice, but the function problem is virtually identical, except instead of a matrix acting on a vector, you have a bunch of derivatives acting on a function. And you want the function back, and in that case, the physical meaning of the eigenvalue is that of the energy. I plucked the simplest possible, probably this is really the simplest possible energy operator from quantum mechanics, and that's a second derivative, so you can kind of figure out what's coming roughly in there, the rest of it, and this is a classical problem that second years have seen a few times by now. Okay, I put that derivative in, and that's the equation. It's a differential equation. I'll teach you how to solve them in a couple of lectures from now, but for now I just simply guessed the solution. I said, okay, it's a second derivative. You want the function back after a second derivative, it must be trigonometric. And so, well, I wrote you a function. You can just quickly check by substituting it in there, but that's a solution. We have physical requirements on the particle, and these physical requirements, you see in here, when we demanded the determinant to be 0, we put in a philosophical requirement is that we want the solution to be there. In here, we put a philosophical requirement that the particle must be confined to a box, meaning that it has to be the amplitude of the probability test must be 0 at walls, because it cannot penetrate the wall. Okay, so we put those conditions in, it transpired immediately that alpha must be 0, and so the cosine term disappears. We are left with the sine term, and we put the other philosophical condition in there that it has to be 0 on the other wall. A few simple mathematical transformations convince us that this can only be true for specific energies. So either the particle actually has this energy, or it will be forced into the wall, which we demanded to be impossible. And so that makes what's called quantization, where the particle has a few distinct energies, and that's really the foundation of quantum mechanics. The first time this was noticed, people started suspecting something. Max Planck, I think it was. And okay, we put that energy back into here, simplify, and we get the corresponding eigenfunctions, which in a few lectures' time I will teach you how to normalize. Okay, so this is the entire picture of the eigen problem. You will have plenty of practice with it in your workshop, and you will see it at least 4 or 5 times in your different physical chemistry courses. Any questions?